Hello and welcome to anyone tuning in to our video on cyclic motions and simple harmonic motion for IB Physics HL. In this video, we'll be going over 4 questions that help apply knowledge to exam-style questions. So, without further ado, let's get started. First of all, I will start off from a little reflection on the last topic that we discussed, cyclic motion. However, in this video, we will focus on the application of cyclic motion, where we will consider the orbital motion of a satellite. The equation we will use for the cyclic motion would be the same equation mv squared over r. However, for orbital motion, we will equate it to gravitational force, which is gmm over r squared. Question 1. A satellite orbits around the Earth above the equator with a period equal to 24 hours. Determine the height of the satellite above the Earth's surface. First, let's draw a simple diagram that shows a satellite orbiting a planet. Here, the force acting on the satellite is the force due to gravity and no other forces, assuming no friction. Now, if the satellite is able to induce enough velocity v perpendicular to the force in order to sufficiently orbit at that specific height, the satellite can orbit around the planet. Now, with that in mind, assuming the satellite is in orbit and that the orbit is circular, the equations introduced at the beginning of this video can be equated to find equations for v or r. Additionally, for this question, the Earth's radius and mass is given to us. The radius is 3.6 times 10 to the power of 7, and the mass is 5.9724 times 10 to the 24th power. So here, I will start by finding the equation for v, and considering what we are asked, to find the height of the satellite, which would be r in this case. Given the time period t of the orbit, v can then be broken down into the expression 2 pi over t, and by doing some simple algebra, the expression for r becomes t squared gm over 4 pi squared, all cube rooted. Since g and pi are constants, the remaining information necessary is m, which is given in the question. However, once we find the value of r, that is not the end of the question. The question asks for the height above the Earth's surface. So, by subtracting the other information given in the question, the height above the Earth's surface can be found. This would be the end of the question 1. However, one thing to keep in mind would be to read through the question carefully. If there is some data that you think you may not use, since the data is often given in order to solve the question. Question 2. A car of mass 820 kilograms lowers by 5 centimeters when an 80 kilogram man gets on it. What is the spring constant for the shock absorbers of the car? Part B. Estimate the frequency of the up and down motion of the car. First, we want to make sure that we can write the correct free body diagram. We draw the car as a point mass, indicated by a dot, and the force acting downwards is the weight of the car and the man, where the force opposing it is the force of the spring. Even though the car is moving up and down, the whole system is not accelerating when we see that the oscillation is part of the system. Therefore, the net force acting on the system is 0, and therefore, the length of the arrows indicating each force is equal in opposite directions. We also know that the force of the spring is kx, where k is the spring constant and x is the length of extension. Because the downward component of the force and the upwards component of the force is equal, kx is equal to mg. In part way, we are asked to find the spring constant, and therefore, by rewriting this equation, we can see that the spring constant k is equal to mg over x. By the given values from this question, we can compute the spring constant to be 176,580 newtons per meter. This question has all 3 values in 3 significant figures, so the final answer to part A of question 2 would be 177,000 newtons per meter. Part B of the question is again simply plugging in the given values in the formula given in the formula booklet. The difficult part of the question, though, is to find the correct formula we want to use. The known values that we have are the mass of the car and the man, the decrease in height of the car, and we also know the spring constant from part A. We are asked to find the frequency of the up and down motion of the car, and the formula we want to use here is T equals n pi root m over k. Pi is a constant, so we know the value for it. M is mass as given in the question, and k is found in the previous section. So this formula is perfect. Because we know that F is equal to 1 over T, we will have to start by finding T and then solve for F. Notice that the mass of the system is not only the mass of the car, but also the mass of the man as well. So it's important that we don't forget to sum up the masses to use here. By inserting the numbers, we know that T is 0.449 seconds. Remember, T is the time period of the oscillation, so therefore the value of 0.99 seconds reveals that the car moves up and then down and back to the original position after 0.449 seconds. Well, that's the wavelength of the oscillation. Notice here that the amplitude is decreasing, and we can say that the oscillation of the system is damping. And one interesting fact about damping of a simple harmonic motion is that the time period never changes. Try it out. Using a homemade pendulum, we're not done with the question yet. We need to find the frequency, not the time period. That's where many students make stupid mistakes. Not worth dropping your marks. By using F is equal to 1 over T, the final answer for this section is 2.23 Hertz. Question 3. This question is about simple harmonic motion. The midpoint of a guitar string executes simple harmonic motion with motion following xt is equal to a cosine wt. It has an angular velocity of w equals 3.01 times 10 to the power of 3 radians per second, and an amplitude of a equals 0.92 millimeters. A. What is the maximum velocity of the midpoint during the motion? B. What is the maximum acceleration? And C. What is the frequency of the guitar string? This question is pretty simple as well, by which we just have to make sure we know what formula to use, and we're just going to plug in the known values into it. Maximum velocity equals the angular speed times the maximum displacement, or the amplitude. Hence, we know that the maximum velocity of the guitar string is 2.6792. Here, we have two graphs of displacement versus time and velocity versus time. From the diagrams, we know that the velocity is at maximum when the displacement is at 0, and this is a very important thing to take note in simple harmonic motion. Part B. We are asked to find the maximum acceleration of the string, and here we'll use the formula in our formula booklet to find the solution. The acceleration of the string is omega squared x initial is equal to 3.01 times 10 to the third power all squared times 0.92 times 10 to the negative third power. The acceleration of the string is 8,330 meters per second, and it is indeed a very fast acceleration. We can kind of justify this. When we see guitar strings, we can see that they are indeed vibrating so fast that they're hard to see, which is caused by the very large acceleration of the string. Here, we have the diagram of displacement versus time and acceleration versus time. Remember, the formula of simple harmonic motion is A is equal to negative omega squared x. And as we can see here, a negative sign shows in the graph that when displacement is at positive, the acceleration of the graph is negative, and vice versa. Hence, it's also important to remember that the restoring force acts on the opposite direction of the displacement. So, we are wondering, with this high acceleration, how many oscillations are there in a second? We're asked to find the frequency in this section, and again, we'll be using the formula omega is equal to 2 pi f, and reorder them to find f. The frequency is found to be around 479 Hz, and that will be the solution to part C. 479 Hz means that in every second, the guitar string does 479 sets of oscillations sideways, and that is very, very fast. That's why we barely see them with our naked eyes, and we use slow motion videos to watch them. Question 4. The cane and dust cap D of a loudspeaker L vibrates with a frequency of 1.25 kHz with simple harmonic motion. Determine the total energy. First, in this question, we'll draw a diagram to represent the loudspeaker L and the dust cap D. To solve this question, we'll need to find the equation for total energy, which is expressed by half m omega squared x initial squared. The total energy in a system can be found by adding the kinetic energy and potential energy. By using the equation for total energy, we can get half times 4 pi squared over t squared times m times x initial squared. This can be simplified into half 4 pi squared f squared times m times x initial squared. F in this case is frequency. By substituting all the known values in, we get a total of 0.145 joules. And there we have it. If you found this video helpful, please feel free to see some of our other content explaining IB math or physics through our channel. Thank you for watching, and we'll see you next time.